And I'm going to talk about Tcl FlightAware, kind of an overview of a lot of stuff that we've done and are doing. I've read that when first creating Facebook, Mark Zuckerberg used PHP, and that Facebook is still really heavily PHP, although they built a fancy compiler for it. I reckon his motivation was expediency and familiarity. He was in a hurry, PHP was there, he was familiar with it, and he was able to get up quickly. I'm not trying to compare us to Zuckerberg, just to say that I understand being in a hurry. When we started FlightAware in 2005, we wanted to get going as quickly as possible with as little work as possible. Oh, wait a second. I want to say a little thing about FlightAware. FlightAware founded in 2005, so we're pushing toward 14 years old. Headquartered here in Houston, Texas. We're the largest provider of flight tracking data to airlines and private aviation, and we have 85 employees, mostly here in Houston, but also in New York and in the UK and in Singapore. Okay, so let's go back to 2005. 3 guys, an FAA feed, the internet, and a ton of ambition. So when we started, we wanted to get going as quickly as possible. We knew that we wanted to use a scripting language. We knew that a lot of work we would be doing would be web-centric, and that we wanted to heavily leverage SQL. Daniel Baker and I had already been using FreeBSD, Apache, Tcl, and Postgres at our prior company for server-side web development, and we were pretty happy with it. So it was a simple decision to take all that technology and experience and use it as our starting point. Everyone's heard of the LAMP stack, consisting of Linux, Apache, MySQL, and PHP, or some people might substitute Perl or Python for the P. We called what we were doing FAT-P, which was FreeBSD, Apache, Tcl, and Postgres. For us, it was expedient, it was familiar, it was wicked familiar, it was deeply familiar. We already had user management. We could make HTML tables from SQL query results. We were pretty confident that that approach would scale. And we knew it was solid. You know, correct programs that produce incorrect results due to bugs in lower layers of the system, such as like the implementation of the interpreter, those are schedule killers and they're morale killers. This is one of the hidden costs of trying to jump onto the latest technology. It's immaturity. There are other costs that I won't go into. So we were sold on SQL, and specifically Postgres. We were not fans of MySQL, and buying an Oracle license was and is financially out of the question. We were sold, at the time anyway, on FreeBSD. We were firmly in the Unix style open source camp. We wanted to license as little software as possible. We didn't want to spend any money, if you didn't get that inference. We wanted to have the source code to everything. A lot of times you don't need the source code, but boy, when you don't have it, you know, and you do need it, it really sucks. So having all the source code to Tcl source, to Postgres, to FreeBSD, that was a plus. We wanted a flexible architecture where besides making web pages, we could write event-driven programs or straight declarative ones. We weren't fans of Perl nor of PHP. In particular, I didn't like the look of server-side PHP programs because they looked like HTML to me. So Tcl it was. Once we got a feed from the FAA, we used Tcl to parse it and begin to try to make sense of it and writing stuff about flights into the database. And it worked. Let's go back to 2005. So one of the first things we got going was this Tcl program that would connect and read the data from the FAA and store it to disk in its native format. Another Tcl program would read those files and decode and interpret the messages in them and update the database and whatnot, other stuff besides that. Within weeks, working on nights and weekends, web page code written in Rivet, which is just HTML with embedded Tcl, it accessed the database and produced web pages about flights, about historical flights, and airport activity. While the handful of incumbents could show you only the last position of the current flight for a flight, we could show you the entire track. While they could tell you only about the last flight, we could tell you about every flight we had ever seen. We hadn't seen a lot, but we could still tell you about the ones we had seen. It was better than anything else out there, and I'm not kidding. We were doing a secret open beta where we told people, hey, here's this website, FlightAware.com, come check it out. Let us know what you think about it, but hey, don't tell anyone else. That was the secret part, don't tell anyone. Well, someone forgot to tell someone not to tell anyone. And so one morning we got up and we discovered we'd had several hundred users register overnight, which was insane. I thought we were being spammed or something at first. It turned out that someone had posted about FlightAware to a Microsoft Pilots mailing list. And hundreds of people at Microsoft registered. This was fortuitous. Since the site had become public and was suddenly getting a lot of attention, it gave us a sense of urgency to improve it as quickly as possible. The response was amazing. We went to the big annual aviation show and we were mobbed. We had actually been to shows with the prior company where we would stand there at our booth, where we had paid tons of money and we would just beg people to talk to us. So it was a crazy experience of just a huge line of people wanting to talk to us, either wanting to do business, wanting to tell us how much they enjoyed us, or asking when we were going to start charging. And then we would say, we're not for the website anyway. So we also kind of knew that our stuff sucked, and we wanted to fix that. And I'm going to show you kind of how much it sucked here. I'll pull this off. Yeah, this is what the website looked like in early 2005. You can tell that engineers did this. These are HTML tables with the actual table borders and stuff like nobody ever uses. And so that's what it looked like in early 2005. A little later in 2005, it was a little nicer. We didn't know how to make things that were pretty, but we knew what pretty was, so we found someone who knew how to design. Now we actually have designers who work at the company. By 2006, it was getting a little better, and then by 2008, legitimate design involved in producing the website. And if you look at the site now, I think it's pretty nice. So while all this was going on, we were trying to understand flight tracking. There were a lot of mistakes and errors in the data feed. After all, a lot of the data feed is just stuff being typed in by air traffic controllers. There also wasn't any kind of unique ID for each flight, and this was very problematic, it turned out, because there were flights flying around with the same ident. Like there was an Air 1 in Honolulu, and in Chicago, and in New York. There was a EGF 104, American Eagle, was real common at doing that, and even United would have UAL-5 flying from London to Houston, and another UAL-5 in the air at the same time flying from Houston to New Orleans. So that caused us to draw some very funny tracks and things at the beginning. So the original program was naive and it was not stateful enough, so we wrote a new one. And that program we called the feed interpreter. The feed interpreter would read the feed and it would keep track of flights and it would match flights to flight plans. It would assign a unique ID to each flight, and it would normalize them, and it would make every flight have a departure message, even if one hadn't been issued by the FAA. All right. If everybody's phones go off, we'll deal with that too. All right. So, we would create messages synthetically if we didn't get a message. So by the time the feed interpreter had finished looking, at these messages, like maybe it would see an aircraft climbing near an airport, but we had never seen a departure message, so it will generate a departure message, and then all flights will end one way or another. They arrive in a way where we say, well, we don't know what happened, but it can't be flying anymore. So we call that a flight results unknown arrival.
Lead to a bite.
We created a format for storing data called daystream. It stored one file per day, and it had a directory structure above it of years and months. We had an Tcl class that wrote the daystream files and put a switch line at the end of each day. It determined when the day had changed, the UTC day had changed. It started the next file. The writer has no idea. The writer just says, hey, I want to write this daystream feed. Here's a message, here's a message, here's a message. Behind your back, the Tcl class will handle the day switches and write the switch files and the switch lines and do all those things without the writer's awareness or intervention. A different Tcl class was the daystream reader, and so it made the daystream data available to a program that wanted it through callbacks, finding the files locally or streaming them over the network if the files were remote, and it automatically would switch days without the reader having to know anything about it or do anything about it. So this has been and continues to be the backbone of how we read and write and chain the processing of flight tracking data. We began looking at integrating additional data feeds, because at first we were just the US. We didn't have airline schedules and things like that, so we wanted to add airline schedules. Then we wanted to add data from European air traffic control authorities, then from Australia and from New Zealand. So we began to look at how to do that. There were a lot of differences between the feeds. Some would use ICAO format for things, the International Civil Aviation Organization, while others would use IATA, the International Air Transport Association. So we would translate everything to ICAO because we decided we would be ICAO. The first thing was always to write the data to non-volatile storage and in as close to the native format as possible. By as close to, I mean that we might in some cases have to write framing information around the data, but we always endeavor to keep the data in the native format, as sometimes we discover that after importing and translating the data, there are bugs in our code or misunderstandings in our reading of the specification, and if we didn't keep the data in the original format, we would have lost fidelity. So we can always go back to the original format and, oh, now I understand, this bit means this, and stuff like that. Next, we make a translation pass to conform the data to the standard format and to make it into key value pairs, which we're big fans of. Most feeds are received by Tcl programs, although with a few of the newer feeds we're using Java because it's JMS and it gives us JMS compatibility with the sender. Next, a Tcl program called the Combiner would subscribe to all these feeds and order them roughly in clock order as they come in and produce a single combined output feed. And then the feed interpreter would read that, and guess what it did? It interpreted it. This is a trick question. As message rates and the number of flights and the number of data sources grew, and as our own data network grew as well, the single-threaded feed interpreter could no longer keep up. We not only needed to make it faster, we needed to make it a lot faster to provide headroom for reasonably quick catch-ups in the event of an outage, and to provide additional capacity to process more messages, and to do a heavier amount of computation per message. We thought pretty hard about how to partition the data and shard it. One would be like by geography. So you might have a United States and a Europe and stuff like that. But that had some big problems for us as the planes would move from one area to another, and the amount of data that we'd have to forward, and the fear that if anything went wrong, the whole edifice would just lock up. We experimented with Cassandra and we found out it wasn't flexible enough. Cassandra's kind of interesting because it has this thing called CQL, the Cassandra query language, and it looks a whole lot like SQL, except it has all sorts of crazy limitations. So you can only order by certain columns, you can only do comparisons on certain columns. If you realize it's just like a really smart key value store that has some query capability, then you're okay. You start thinking it's a replacement for SQL, you're going to be sorry. So we settled on using shared storage between multiple child processes through Postgres, and we call that Hyperfeed. This was created and maintained by our flight tracking team, all of whom are here at the conference, and ZapCon presented on Hyperfeed at last year's conference. All this is Tcl. Okay, so when message rates began to approach the capacity of the combiner, we looked at various ways to make it go faster. In the end, the flight tracking team created H-Combiner, the feed combiner implemented in the Haskell functional programming language. So we're not, ultra doctrinarily Tcl. We're willing to do whatever we need to do to get the results. So the output of Hyperfeed is the control stream feed, which is the normalized source of data after all the other applications read. So these applications include updating the database, updating the track database, making streaming feeds available to customers who receive them, like B2B data feeds, generating the website, generating alerts, to generate millions of alerts a day on things like aircraft departure, arrival, certain minutes out, etc. On the website, it's almost all Tcl. Tcl code is the interface between the general database servers, the real-time database, Popeye, the tracks database servers, and the web servers. We have a FlightXML service to allow querying of real-time and historical data, and we have Firehose feeds, as I mentioned, which are real-time and historical streaming feeds. Even most of our stored procedures in the database are written in Tcl in a Postgres thing called Tcl. It's been handy to have commit to pgtcl, by the way. And we've also managed to get some improvements to Tcl pushed back through into Postgres, which is a surprisingly difficult thing to do. These guys are very, very picky, although as a user of it, it makes me really happy because Postgres has very few problems and very few crashes or weird behaviors or regressions. I think Tcl has stood up well to these challenges, and only a handful of times in all these years have bugs in the Tcl implementation caused problems. A recurrent pattern as the data rates and contractual playback rates have gone up to these very high levels is the need to heroically speed up Tcl programs or rewrite them or rewrite parts of them in faster languages such as C++. In some cases, algorithmic improvements and recoding critical paths as Tcl extensions written in C++ have been very successful. Our multicom alert system went from slamming a dozen high-end 24-core Xeon machines to lightly loading just 2. In other cases, there was no way algorithmic improvements alone could solve the problem. Due to performance demands from an important customer, we needed to retrieve, examine, and forward subsets of message sets at an input rate of hundreds of thousands of messages per second. This was evolved from a first implementation in pure Tcl to one that had Tcl with some C++, to one that had Tcl with a whole lot of C++, and now currently to where Tcl is used to set things up and orchestrate the high-level activities of the program, but the fetching, decompressing, filtering, and forwarding of messages is all done in C++. And the C++ itself is multi-threaded and uses somewhat exotic classes and makes serious efforts to avoid allocating and copying memory and so forth. In other words, even in C++, we did a considerable amount of work on performance. On the web servers, we load 710 packages into Rivet, Tcl packages, that define over 4,500 procs. When we needed to do XML, we tried some Tcl packages, found one that we liked, and started using it. That's kind of been our approach. If there isn't anything or we're not happy with what's available, we'll write something ourselves and usually open source it. Since so often we're needing to speed up programs, we started looking at ways of extending Tcl that are high performance but less difficult to work with than C, even though we're really good at extending Tcl in C. We wanted to be able to write in a high-performance, object-oriented systems programming language and be able to fluidly call our huge body of Tcl code and be called by it. Swift is a really cool-looking language, very modern and expressive. Colloquially, it feels like a scripting language. We did a good bit of work on Swift Tcl, endeavoring to bridge between Swift and Tcl, but we ran into problems. Swift libraries for interacting with the operating system on the server side were minimal. There weren't a lot of class libraries for even relatively simple data structures. Most of the attention that Swift is receiving, including from its developers, is to create apps for iPhones and iPads. Also, Swift was a rapidly moving target, and FreeBSD support was sorely lacking. So it had these tantalizing aspects. Calling Tcl from Swift and calling Swift from Tcl was really transparent. But Swift programs didn't really know they were calling Tcl, which was, and vice versa, which is something we really wanted. So even though we had all these problems, those problems basically killed Swift for us. But it was promising enough that we kept looking. So then Shannon No, who's here, found CPP Tcl, which was a C++ library for creating interoperability between C++ and Tcl that had been written by Maciej Sobczak in the mid-2000s. Kind of just, I had never heard of it. I don't know if anyone did. It was an amazing piece of software that I think just kind of quietly passed by. Shannon found that and revived it, and it's become a super important technology for us, and Shannon is going to be presenting about it here at the conference. Suffice for me to say that Tcl developers can use C++ to create high-performance code that leverages all of the C++ ecosystem while providing dead simple ways to bring their C++ functions to Tcl with expected Tcl semantics and no funny business. No funny business meaning like if you've ever used Swig, that's funny business. Like the error messages are really difficult to understand and things like that. So that's what I call funny business. Writing C++ extensions for Tcl using CPP Tcl is vastly easier and requires far less coding than extending Tcl in C. So CPP Tcl is everything I'd hoped Swift Tcl was going to be, except for C++ is a little bit clunkier than Swift. Nonetheless, we have a good bit of in-house C++ experience and we're putting it to good use. We push out software to servers with Tcl. We monitor applications with Tcl, among other things. So last, I want to talk about flight feeders and FlightAware, and then I'll just summarize. Here's a diagram of hyperfeed. What is that for marketing? Oh, these are just some beautiful pictures that Shannon and Ann Leslie made. These are heat maps of surface movement positions. I just wanted to put them in there because I just think they're so great. You can see the entire structure of the airport there from positions that we read from aircraft moving around at the airport. Okay, so this is a flight feeder.